So without further ado, I would ask Marc-André Beck to come to the stage. He's been working on micromobility for the past 14 years. He's the CEO of Grivix, and they're based in Switzerland. They focus on extreme high-power charging tech with cooled cables, automation with robots for charging applications. Ladies and gentlemen.
Thank you. Good morning. So I have the presentation today about MCS and what's next. What do we do after MCS? But let me quickly introduce myself and the company. So I'm in electric mobility since 14 years, and just to give you an idea of 14 years, there was no Tesla back then on the road. I mean, there were still only combustion engines. And back then we were ripping out combustion engines out of vehicles and putting in electric motors. And we built our own battery packs, which are horrible and dangerous, thinking what we did back then, but still they're on the road. Now, 14 years later, we are doing autonomous megawatt charging technology, so we are creating specialized cool cables for extreme high power charging. We are doing that with simulation, and we are doing automation of charging so that vehicles, the driver doesn't need to get out, and we do that fully automatically. Why we do that, that's a question I will answer a little bit later. But first, I have a question to the crowd here. And you all know we have CCS up to 500 kilowatts. We have MCS somewhere at 3.75 megawatt. And my question is, how much is enough? So where do we need to go? How much power do we need to transfer in the future? To give it to the person there in the yellow shirt. He's smiling.
Thank you. No clue what future brings.
No figure, 10 megawatt, 20?
Yeah, it depends on the transportation methods. If we're going to charge planes, then it's going to be really high. But is that the future? Sorry. If we need to charge planes, then yeah, who knows what brings it, but I have no clue.
Okay. There's a person just right behind you.
Yep, for lorries and buses, at least a megawatt. Ships are also charged. Quite thick cables. I'm not quite sure what that is, but it's probably over a megawatt.
Sure.
I think I'm just going to agree with him. With airplanes, we'll probably need more than a megawatt if that comes to fruition.
Maybe Marco Pifaretti here also has a comment, the gentleman with the red shirt. So Marco, how much megawatt will we need in the future?
5.
Very clear answer.
30 megawatt for ships.
30 megawatt for ships. Okay, I'll leave it for the moment. I just want to give you a quick overview where we are nowadays. We are with MCS, and I don't know if you see it very well. If you compare a gasoline station usually pumps at 23 liters per minute, and that gives you a total energy of 13 megawatt. That's a regular pump station, a gasoline station that you will find anywhere on a highway or wherever. And if you're looking at the losses and the efficiency, you come at roughly 2.6 megawatt. So if you have MCS nowadays with 3.75 megawatt, then we already solved the problem, right? We are already faster than filling in gasoline with MCS. So all fixed, we can go home, problem solved.
Can I ask?
So where are we today with electromobility? Currently, for passenger cars, we are 200 kilowatt. For heavy-duty vehicle, as it was said before, we are roughly at 1.5 megawatt. Then we are in mining. There's a demand currently at 12 megawatt. We are working with shipyards, and there's the demand somewhere between 60 and 100 megawatt. I mean, the market is changing. Right now, we only thought about batteries, but in the future, if you want to electrify the whole mobility, we need to think about the whole range. And also, batteries became better. I made a little statistics and showed that batteries in the last 15 years in passenger cars have grown by 2.5 times. And charging speed increased by 6 times. So in the last 15 years, vehicles charging speed increased by 15 times in total. So if you think about that from now into the future, then we would be in a megawatt range for any passenger cars. I don't think we were going to end up there, but it's a good thing to think about that it's not the end what we have currently, and 200 kilowatt is not going to be the limit. So even though we have 3C right now charging for passenger cars, we have 6C charging with Titanate batteries, which is quite used in mining. There are startups that already have shown charging at 60C currently in the laboratory. Now you say, okay, that's laboratory, who cares? The thing is, if it's shown now in the laboratory, it will be in 7 years on the market and in 10 to 12 years on the highway. So then we talk in 12 years about fully recharging the vehicles in 1 minute. And imagine what energy transfer we need to do that. And keep in mind, vehicles have a different cycle than infrastructure. Infrastructure is being built for 15 years plus. Vehicles are built for at most 7 years. So that's my question, what comes after MCS? And a little bit of a hint, in MCS we don't just have MCS, we also have ruggedized MCS, which is currently already at 6 megawatt, which is used in mining. And our proposal is to create extreme MCS that can be charged, that can charge at 60 megawatt at a size only 70% bigger than the current MCS connector. And how will we do that? I mean, we need to make bigger cables or cool better or do something right. And again, here I have a little bit of a thought process. Of course, we don't need cooled cable. We can also use uncooled cables. And if you do it for CCS, a cooled cable, which is nowadays in the field with a diameter of 34 millimeters, quite flexible. You see them somewhere around here. At 1.4 kilogram per meter. That's quite usable. If you do the same thing with an uncooled cable at that rate that is continuous charging, it would be already way heavier. But thinking about MCS, where the current cables are a little bit bigger, you've seen the ones from Amphenol. If you do uncooled charging for MCS, then you are already at a diameter of 12 centimeters, and the cable would be 32 kilogram per meter. So it's not really operatable anymore. So definitely, we need to cool. So we need to get rid of the heat. The problem is, if we increase the current, and you have two options here, whether you increase the voltage or the current. So if you increase the current, the problem is that the energy dissipation grows in square. That's a bitch, right? That's exponential. We don't like that. So the power losses become quite extreme in a very short time. Additionally, we can do something else. We can increase the cross-section, but we already showed before, the cables become too heavy. It's not going to work. And also, if you have a very small diameter of the cable, with a very small cross-section, we have another problem. So at CCS, if I turn off the cooling system, it takes me 9 minutes until my copper starts melting and the charging station explodes. It's not really going to explode, but it's going to do funny stuff. For current charging station with MCS, it will take approximately 4 minutes. With the ruggedized MCS, it only takes 2 minutes. And if we continue this thought process to our proposal to go up to 15,000 amps, it will only take 22 seconds until stuff gets really nasty. And by really nasty, I mean melting copper flying around. So that's where we come to an end. And we have figured that 15,000 amps is possible. We can build that. But it's kind of also the reasonable end that you can build. And one thing that I often hear, yeah, no problem, we can do automation, we can use robots, but robots have another problem. They are never all three things. They are never strong, fast, and precise. You only always get two of these three things. So you think you can take a big robot with a big cable? Sorry, it's not going to work. We need to still to cool. We need to cool it. Okay, then we have the other possibility. We can increase the voltage, but going above 1,500 volt, again, it's not going to work because it's dangerous for humans. Still, heavy-duty vehicles are already operating at more than 3,000 volt. So here in the vehicles, we have maximum 800 volt, but in mining or trains, it's already 3,000 to 4,000 volt. So in the railway, the Italian railway industry, we are currently at 4,000 volt DC maximum. But again, we have the possibility to automate. So if you go for higher voltages above 1,500 volt, there's no way around to automate our charging. So what we have done at Grivix till now, we have created a connector, simulated it, that can run at 4,000 volt, at 15,000 amps, and it's less than 70% bigger than an MCS connector. We are working currently on that to make it ready for standardization drafts. And again, here I want to stress very clearly, it's not magic. We don't need to have a new connectivity systems or motor that are, yeah, whatever. I have seen very strange things for connectors that you can do. These things are going to be quite small. It's not going to be much bigger than MCS, and still we will run it at 60 megawatt. We've seen that the compromise for the maximum current will be around 15,000 amps and 4,000 volt, but still automation will be mandatory. And one question that you're most probably going to ask later, yeah, how do you do that? How do you get 60 megawatt to the charging station? And say, no, it's not a problem. Our company starts selling nuclear plants with our charging stations. No, not really, but you need to create DC grids with batteries, otherwise things are not going to work. Again, that's a summary of what I said before. You said, okay, you have now these huge cables and they create an enormous amount of losses. Yes, they do. So already at CCS, we have 1.5 kilowatt thermal loss, which is a lot. With MCS, currently we have 6.5 to 25 kilowatt heat loss. I mean, you can heat more than one house with just this heat dissipation that you have from these charging stations. And for our extreme MCS, we planned something like more than 200 kilowatt heat dissipation. It sounds like extreme, a lot, but then you look at the losses, at the efficiency losses that we have for cooling, and it's a lot under 1%. So even though these figures are huge, losses are very, very small. So that's already the summary. Charging at 60 megawatt is possible with nowadays technology. It doesn't need something very, very sophisticated or new. We have it at hand. Infrastructure definitely needs to be upgraded. You cannot run the infrastructure with the current infrastructure. Just to give you an idea, the village I'm living in with 12,000 inhabitants has 13 megawatt continuous consumption with a lot of industry. So if I put one of these charging stations in place, then we have no electricity anymore in our village. And definitely automation becomes a requirement, and not because Elon Musk promised us autonomous vehicles, but because it's absolute requirement for the future drivetrains to really charge fast. Thank you.
I think we can open for questions.
Would it be possible to do something useful with that heat?
Of course, you can create a remote heating system. It's just a little bit of a problem that all our customers currently are in a desert where you do mining. But yes, in the future, if you go back to Berlin for fast charging and for airplanes, yes.
what is the theoretical max for passenger cars at which they can be charged?
I mean, the limit is the battery and not our technology. I mean, with our technology, you could charge it with 60 megawatt, but you will never find a battery that can swallow that amount of energy that is big enough and that can be charged fast enough currently. But as I said in the presentation before, technology will evolve with batteries, that you in the future, in like 15 years, will be able to charge vehicle batteries in 1 minute.
Yes.
Thank you. How do you plan to integrate different charging rates depending on what is required at the time? Will it be also storage or feeding back into the grid? How will you try to operate the curve?
So that I understand correctly your question, it's about the grid management, right?
Yes, grid stability, but also your capability. I mean, 60 megawatts is not going to be what you're continuously using.
No.
And that's a massive difference between on and off, if you like, depending on what is charging. So how are you going to integrate storage, for example, peak shaving, etc.?
We are working in Switzerland on a white paper how to build DC grids or DC microgrids for the future to enable this fast charging. So basically our proposal is that we create grids at 4 kilovolt and put batteries in parallel at different spots around the charging area. So if you think of a mine, you instead of having an AC mid-voltage grid, you create a 4 kilovolt DC grid and have batteries at different spots, which will allow these peak currents to be charged. Otherwise, you cannot do it with the regular mains that will break the system.
I think the gentleman in the jacket had a question earlier. Maybe you'd like to give it a go.
I just had a comment on the charging power, which is done by the gasoline cars, petrol. I think it is just a continuous charging with the liquid, but we need to take into consideration of our charging curve. So if we say, for example, 2.6 megawatts charging, maybe it is just 10 minutes or let's say 15 minutes of the charging according to the battery capacity of the vehicle. So maybe we need to get the average of the total liquid, let's say, fueling, and then also charging. We need to compare the averages, I think.
That's absolutely correct, but what I was presenting here was the capability of the charging station and of whatever the battery can swallow. That's what I already mentioned. With the batteries, we are not there yet, but also batteries will evolve. Maybe not 60C over the whole charging cycle, but maybe 60C, and then you have at 80% a reduction to 20C. But that's will be more than fast enough in the future.
Yes.
Further to my earlier point, do you think there will be charge sharing, as has been in the past, where you fluctuate the charging rate depending on how many users you have, also to have better efficiency of your system, so that you don't have max charging maybe, but you have fluctuating loads that are agreed with the vehicle charging?
Our proposal that we have with the DC grid is just average it out with batteries in parallel, and we don't care. So basically our proposal is also just add as many solar panels as you can and just charge but you need to have a buffer in between. It's really hard to manage the whole grid. Maybe Landesgier can show us how to do it. That's one company just behind there, how to manage a grid, but to my knowledge it's quite hard.